Hello everybody, this is Mr. Arocena, and on today's lesson we're going to be talking about polar bonds and molecules. Okay, what is a polar bond? This is a special type of covalent bond where the electrons are shared unequally between the atoms. So you can think of it as one atom is more prone to having the electrons near it than another atom. What this effectively does is, if you can think of it, if you have a covalent bond and you have two elements like so, then the electrons in this pair, if the bond is polar, they tend to want to hang out closer towards one of the atoms. So that's what bond polarity is, when electron sharing is unequal. Okay, they're still sharing it, like this, like we'll call this atom 1 does not fully take the electrons from atom 2. It's just that atom 1 is, I guess, wants the electrons more, so spends more time with the electrons than atom 2 does. Okay. Now what this does is during the lifetime of the molecule, it actually gives one part of the molecule, or at least in this case of this two-atom bond, one of the atoms ends up being more electrically charged than the other one, because the electrons are hanging around this one more so than they are this one. So this one has more negative charge. And that basically means then that in this particular molecule, it's a covalent molecule and it's supposed to be sharing evenly, but this atom 1 doesn't share as evenly as it should, so therefore atom 1 tends to be more negative than atom 2. Okay. So when this happens, the overall molecule, or at least this bond, one side of the bond ends up being slightly negative and the other side ends up being slightly positive. Okay, but not to the same extent as an ionic bond. Okay, so we'll just put down here slightly negative and here slightly positive, because again, atom 1 hasn't fully taken the electrons, it's only taking them for most of the time, and atom 2 gets the electrons sometimes but not all the time. Okay. All right, so this leads to what are known as polar covalent bonds, and that's, again, so like what I was saying, it's when an atom attracts electrons more than the other atom does. This will usually occur if one atom has very high electronegativity, and this term, electronegativity, just means more likely to attract electrons. More likely to attract electrons. Usually this will occur with larger molecules. Oops, not molecules, electrons. There we go. Because one of the things that makes an atom more electronegative is simply how many protons it contains, because the more protons it has, the more positive charges it has, and therefore it has more ability to attract electrons. But if the atom is too big, then there will be more electrons, because as we know, as the atomic numbers go up, the number of electrons also goes up. So more electrons and more atoms or more protons tend to lead to not necessarily higher electronegativity, but definitely it helps to have lots of protons when dealing with electronegativity. Textbook page 177, this shows a table of electronegativities for, I think, the first 20-ish elements. And it'll help you determine whether something is going to be a non-polar covalent bond or a polar covalent bond. If the differences end up being really high, so if electronegativity difference is really high, like over 2, then what ends up happening, if it is greater than 2, then the element, or not, the bond is ionic. because it basically means that one element or one atom has completely stripped the electrons from the other atom. It's no longer a sharing, one has physically taken it from the other atom. Okay? So that's how you can tell whether something is polar covalent. And sometimes when we draw the polar covalent bond, we can show it. So if I have an atom like this and an atom like that, I can show the polar covalency of the bond by drawing this is a bond, or I guess an electronegativity arrow, and this shows direction of electron movement. Direction of electron movement. So the arrow shows us where the electrons are more likely to show up, or where they're going to hang out more, where the electrons are more likely to hang out. Okay. So that's what a polar covalent bond is. Now what this does is leads to, it can lead, polar covalent bonds can lead to what are known as polar molecules. So a polar molecule is a molecule that has polar bonds, and what this ends up doing is that if the polar bonds are arranged properly, then the molecule will have an overall positive end and an overall negative end. And what this means is that the molecule can then be affected by electricity, because it acts like, it's sort of like an ion, but not quite. But because of the way the electrons are arranged, part of the molecule will be positive and part of the molecule will be negative. Okay, so if you pass electricity through it, then the positive end of the molecule will move to the negative electricity or negative electrode, and vice versa. Okay. So if you were to pass electricity through this or have an electric field nearby, then the molecule will be affected by electricity as per the laws of static electrical charge. Okay. Now, how does a molecule become polar with the presence of polar bonds? Well, let's take a look. Okay, so let's do the best example of a polar molecule is water. So I'm going to draw water. There's oxygen. Okay, there's that. So here's water. Now, we already explained in a previous lesson why water has this bent shape. But if you look at your electronegativity charts on page 177, I believe oxygen has a much higher electronegativity than hydrogen does. So what this means is that this bond here, the electrons will flow in this direction. So this hydrogen end has a slightly positive end, and this has a slightly negative end. The electrons from this hydrogen will go this way as well. So the oxygen is slightly negative and the hydrogen is slightly positive. And we already know that the oxygen's got two lone pairs floating around back there and back there. So this shows me that this oxygen does actually have quite a lot of electrons hanging around this region. So this region of oxygen is very negative. Okay, not completely negative. It's not like an ion, but it's still somewhat negative. What this means then is that water has a slightly positive end. I guess in water's case, two positive ends and a slightly negative end. Okay. Because oxygen hasn't fully taken the electrons. The electrons are just more attracted to oxygen, but they haven't fully left the hydrogens either. Okay, now this gives water some interesting properties. Because it has a positive end here, what this allows water to do is it can actually attract negative ions. Okay, so let's just write this in a different color. So this positive end can attract negative ions. Okay, and then similarly, this negative end over here can attract positive ions. And what makes this really useful is water is very good at breaking down ionic compounds because of this. So when ionic compounds come into contact with water, sometimes the positive end of water can attract the negative ions out of the crystal, and similarly, the positive end of water can attract the negative end of water can attract the positive ions out of the crystal. So water can break ionic crystals because of its polar nature. Okay. So this is one of the neat properties of polar compounds. Okay. Now, water, because other water molecules operate in a similar manner, water will actually attract to itself as well. So if I have another water molecule like so, this negative end of the water, this will attract to itself like this, attracts to itself. And you can see this for yourself anytime you have, say, a cup of water and you fill it right full. So if you have a cup of water and you fill it right full, you will usually see the water kind of just like bubble, kind of like bubbling over like this, and not really spilling out if you're very careful. And that's because the water molecules, they attract to each other at the surface here. So the water molecules attract to each other because of that polar nature. Okay. There we go. So the water molecules are all being attracted to other water molecules. And that's due to this polar nature of water, where one part of water is negative and one part of water is negative and one part of water is positive. And as a result of that, they will attract themselves and they will kind of stick together. Right? And this also helps explain the crystalline structure of solid water, because when water solidifies, these positive and negative ends tend to get closer and they will form themselves into a crystalline structure, which is what you see whenever you look at, say, a snowflake or an ice cube or something like that. That's what you see. That crystalline structure is because of this polar nature of water. Okay? Now, that's not to say that all polar bonds will lead to polar molecules, because if the molecule arrangement is symmetrical, then the molecule itself won't actually be polar. A good example is like methane. So I'll draw methane. Methane looks like this. Okay, now obviously it's not the good 3D representation of this, but it's gonna have, well, I'll try to get the 3D representation. It's gonna have a very tetrahedral look to it. So if you remember from the other day, let's see. This solid one represents an electron or a bond pair going out of the page, and then the dashed lines represent them going into the page. No, it doesn't look very good. I'll just draw it as I was doing before. It's easier to see that way. All right, so let's pretend this is my tetrahedral structure. So in this structure, the carbon-hydrogen bonds are polar, which means the electrons tend to push themselves towards the carbon. Okay, but this arrangement is slightly different than water's, because here it's very symmetrical. So this is a very symmetrical arrangement. What I mean by that is that if I have electrons pushing in this direction, so if I have electrons traveling here, and then they encounter these electrons, which are also traveling in the same direction, the net repulsive force will actually push them away from each other. So in this direction, so in the left-right direction, the repulsive forces balance out. The repulsive forces balance out, and nothing happens. So basically, even though the electrons do want to hang out by the carbon, these electrons want to hang out by the carbon also, but they end up getting too close to each other, so they push themselves back. And then a similar thing will happen with the electrons in this pairing up here, and then the electrons down here, is that these electrons will get close and then they will push away. So this molecule, because of the way that the bonds are arranged, you get this symmetrical pushing and pulling, and effectively the electrons stay put. Okay, so here you can write the same thing in the up and down direction. The up-down direction, the repulsive forces again balance out. Repulsive forces balance out. So the electrons don't actually move towards the carbon. They really want to, but because of the symmetry of everything, they don't actually. So therefore, the molecule CH4 is not polar because the electrons don't actually get pushed anywhere. If I compare that to, say, the water up here, because of the way the water is arranged, they're not really this one's pushing this way, this one's pushing this way. They're not exactly opposing each other, so there is a net result of electron movement. In the methane molecule, you have molecules or electrons pushing to the right, electrons pushing to the left, they will cancel each other out. Electrons pushing down, electrons pushing up, they will cancel each other out. And so basically nothing really happens. Okay, the molecule CH4 is not polar, and this was despite having 4 polar bonds. Okay. You can usually tell if a molecule is going to be polar based on its bond angles and how many bonds it forms. So if the bond angles are all even according to your chart, and the arrangement looks very symmetrical, then yeah, it's not going to be a polar molecule. But if there's any kind of unbalanced arrangement of electrons, then yeah, there's a chance it can be polar. Okay. Usually happens with bent models. Usually happens with bent molecules, or trigonal planar molecules. No, not trigonal planar. It's one of the, it's like a tetrahedral, but not quite. Yeah. Anyways, now this polarity explains some of the intermolecular interactions that exist between certain molecules. Okay. So not all molecules will attach to each other. As you know, a lot of covalent compounds are gases or liquids. And that's because their intermolecular attractions are very, very small. Okay. So intermolecular attractions are very, very weak when you compare them to, say, a covalent or an ionic bond. Remember back from earlier in the unit, ionic bonds were giving and taking of electrons, and as a result of that, ions would attract other ions, and they would form crystalline structures until they ran out of ions. Covalent bonds don't need to do that. They basically attach themselves to other atoms, and then they can happily exist as individual molecules. Excuse me. Now, some molecules, they can naturally attract to each other, and they can form larger molecules, sort of like water can attract to itself. Now, the attraction to other molecules falls under 2 types. There's 2 broad categories of molecular attractions. Okay, the first type are called van der Waals forces, and the second type are called hydrogen bonds. Okay, hydrogen bonds are really, really important, especially in biological molecules, and van der Waals forces just help explain why some things are gases and some things are not. Okay. At least at like room temperature. So van der Waals forces come in 2 varieties. The first are called dipole interactions, And these occur when you have polar molecules attracting to each other. So this is like water attracting to itself. Okay, so the positive end of a molecule attracts to the negative end. Okay, so this is what happens with water. Dipole interactions allow or explain why some things are liquids at room temperature, because if the polar attraction is strong enough at room temperature, then the molecules can sort of stick together and they can form a more cohesive substance. Okay. Now, the other type of intermolecular force that falls under the van der Waals category are called dispersion forces. Dispersion forces are kind of like dipole interactions, but they don't exactly follow. Well, I'll explain it like this. So in any given molecule, so let's say I have an oxygen. So here's oxygen. And it's double bonded to itself, like this. Okay. Now, if you remember from the orbitals, both of these atoms have an electron cloud. And based on what we were talking about just at the end of last week, their electron clouds can kind of jumble together and make other electron clouds. Anyways, regardless, the electrons are all kind of floating around here, just zipping along. Now, every so often, the electrons will concentrate themselves around one particular end of this molecule. So this happens every so often. Okay. All the electrons congregate around here for just a moment. Okay. So for a moment, for a brief moment, this molecule is charged. Where normally the oxygen molecule would be relatively neutral, for a brief moment, this molecule has a positive and negative end. Okay, and then for that brief moment, it can then attract itself to other positive and negative substances. Similarly, because of electrostatic attraction, even neutral objects will get attracted to this. So like a neutral molecule, like say a regular oxygen atom, could get attracted to this one because this side is positive and this side is heavily negative. And now obviously that doesn't stay negative for a while because the electrons do zip around randomly. So for a brief moment it'll be like this, it'll attract other things to it, and then the electrons will disperse themselves again, and then the attraction will be gone. Dispersion forces are very, very weak, and they are quite common in a lot of non-polar molecules. Okay. So as a result of this, non-polar molecules tend to be not liquid in nature because the molecules themselves are rarely attracted to other molecules of the same species. Okay. Whereas with dipole interactions, you get the polar molecules attracting the polar molecules, and the molecules themselves can form together to make more cohesive structures. Okay. Now, hydrogen bonds are another type of intermolecular force, and these are only present when your molecule has hydrogen in them. Okay. And what happens here is that the hydrogen, because hydrogen tends to share its electrons unequally with other things, is usually a positive structure. And what happens with this highly positive hydrogen is that it can attract itself to a pair of unshared electrons from another atom. So this is like a lone pair. So if there's an atom with a lone pair of electrons, then hydrogen can get attracted to those lone pair of electrons, because the lone pair of electrons form effectively a large cloud of negative area, and the hydrogen, being slightly positive, is going to be attracted to that. This is highly important in a lot of biological molecules, so like DNA and protein. They have lots of hydrogens, so there's lots of hydrogens, and they have lots of non-hydrogen atoms as well. So here, this oxygen here, let's see, will have two lone pairs of electrons. So this hydrogen is attracted to those lone pairs. Similarly, this nitrogen over here will have a single lone pair, so this hydrogen is attracted to those. So this gives rise to how certain organic molecules are shaped. In actuality, I think in biology 12, when you talk about proteins, the hydrogen bonds that are formed in proteins give rise to, I believe it's the tertiary structure of proteins. The folding of proteins on themselves is due to these hydrogen bonds. And when you break the hydrogen bonds in a protein, then the protein starts to denature and not work anymore. So these hydrogen bonds are very, very important in a lot of biological molecules. Water will also generate hydrogen bonds. So in water, the hydrogen atoms, they have the ability to attract to other atoms because, again, the hydrogen is slightly positive. So if there's any electrons floating around, then this can get attracted to a pair of lone pair electrons on another atom, or sorry, another molecule. Okay. All right, there's hydrogen bonds in a nutshell. As far as which forces are the strongest, the weakest forces are the dispersion forces. They are the weakest, followed by dipole interactions, then hydrogen bonds into ionic, and finally covalent bonds. Covalent bonds are the strongest because you are sharing the electrons. Ionic bonds can be broken by some dipole forces and some hydrogen bonding as well. And dispersion forces are the absolute weakest. So weak to strong. All right. Now, on the topic of covalent bonds, there are actually some covalent solids, covalent crystals that are created with covalent bonds. These are what we call network solids. So a network solid is a covalently bonded atoms, or covalently bonded atoms forming a solid crystalline structure. So they look like ionic crystals. But rather than ionic bonds holding them together, you get covalent bonds. So for example, I think this is diamond. Yeah, I think this is diamond. So diamond is a network solid consisting of carbon atoms which are covalently bonded to other carbon atoms. Because they are covalently bonded and not ionically bonded, all of these carbons are sharing the electrons. It's a very, very strong structure, very strong. Okay, so very strong due to covalent bonding. Okay, we've applied this in other cases as well. So for example, here this is a silicon carbide. Silicon carbide is another very strong solid structure. I think it's used in a lot of industrial applications whenever you need to grind or cut things down. Silicon carbide is, I think, cheaper than diamond and almost as strong. Okay? And these are, again, silicon carbon, and then these would be covalent bonds. Okay, so not ionic bonds. These are covalent bonds, and they are sharing electrons. They are forming a very strong crystalline structure. Okay, so network solids are very strong substances. Okay, very hard substances. Lots of neat uses. All right, there you go. So those are all the different types of covalent molecular interactions. And then we're finishing off with network solids. Your assignment for this section is as follows. And yeah, there you go. Read these pages in your textbook. And again, the table of electronegativities is on page 177. All right. Have a good day, everybody, and we'll see you later.